Hello students, welcome to the class. So today we'll see the theory part 6 of the chapter equilibrium, in which we will be covering the section 6.8. This is the disclaimer. Now in this class our objective would be to explain various factors that affect the equilibrium state of a reaction. So we have various factors like your concentration, like your pressure. So we'll see each of them one by one. How do they affect the equilibrium? If I talk about the specific topic of the NCERT that we are going to cover, so we will cover 6.8 section, in which we will cover factors affecting equilibrium, under which the factors will be the concentration, then we have this pressure, inert gas addition, effect of temperature, and effect of catalyst. So if you talk about the equilibrium restoration, so what do you mean by equilibrium restoration? Basically, whenever you do a change in equilibrium, the system moves in such a way so that the equilibrium can be attained in a quick manner. Now why do we need to attain the equilibrium? So this was basically explained by Lee-Chatterjee's principle. He said that if you change any factor that influences the equilibrium, then what happens? In that case, your system will respond in such a way so that it minimizes or counteracts the effect of the change. Now, why is the system responding in such a way? The reason is that because in equilibrium, the system is in a much more stable state, or you could say it is in a ground state. Now, if you are changing the equilibrium manner, or if you're changing the factors aside it, then what is happening as a result? The system is going to a place where it is having a greater energy. Because why I'm sure about it? Because equilibrium is the most possible stable state of a system, and by changing any of the factor, you will only and only increase the energy of the system, right? So to restore the energy, or you would say to restore the minimum energy criteria, the system responds in restoration of equilibrium. Now some key points you should remember. So Kc independent of initial concentration. So this is a very important point. You can take any initial concentration, but the value of Kc will be same. Second is, changing concentration of reactants and products can only disturb the equilibrium. Again, that same thing. So what does the change in concentration of reactants and products affects? It affects your equilibrium and not your equilibrium constant. Then after that, if you change that or you disturb that equilibrium, the system undergoes some net reaction so that the equilibrium can be again restored. So there are two more factors aside from initial concentration, which are temperature and pressure, which can again alter the equilibrium state. We have talked about this in the previous class, and it is very important to remember that two things are there, only and only two things are there which can change the equilibrium constant value, and those are temperature and the balanced chemical equation. So if you are taking a different balanced chemical equation, by multiplying your previous equation by 2 or by changing the coefficient in any way, keeping the equation balanced, then also you will see a change in the equilibrium constant, and we have talked about it. Similarly, the temperature has a very harsh effect on the equilibrium constant, and we have talked about this Van 't Hoff equation, which explains how temperature affects the equilibrium constant for different kinds of process. Now let me list those factors again. So those were concentration, pressure, inert gas addition. So this inert gas addition is basically the addition of your xenon or helium. Now there are certain conditions under which we add this inert gases. So we'll talk about them one by one. So one is by keeping the pressure constant, and one is by keeping the volume constant. You can add inert gas in two manners basically. Fourth one is effect of temperature, and fifth one is the effect of catalyst. Now I'm repeating this part again and again, and I repeat this thing in this slide also, that your effect of temperature is on both of your equilibrium state as well as your equilibrium constant. Now first we will try to understand in terms of concentration. So what do we see upon changing the concentration? Suppose we are changing the reactants or the product concentration, we are increasing it basically. Now the reaction shifts to the side to use it. Means the extra reactant or extra product which you have added, so you can add either of them, the reaction will proceed in such a way so that your extra reactant or your extra product can be consumed or can be maintained back to the equilibrium. Similarly, if you decrease the reactants or products concentration, the reaction will shift in such a direction. So you have two directions, forward and backward. It will shift in such a direction so that the decreased reactants concentration or the decreased products concentration can be increased again. Let us take an example for the same. Suppose we are seeing here the production of ammonia from nitrogen and dihydrogen. Suppose we take some observations. What are those observations? First is you are adding ammonia. Now if you add ammonia, the concentration of ammonia will increase, right? That means you have now more amount of product. Now to counteract this effect or to counteract this increased amount of product, the reaction will shift backward. And if you will shift backward, it will use the ammonia that you have added. And it will do on until the equilibrium constant has the value of the initial value, or you can say it in a different way, not the equilibrium constant value. The reaction quotient can have a value which is equals to the equilibrium constant, because whenever you disturb a equilibrium, you are now in no position to say that your Q is equals to K. So in this case, if you calculate Q, that will be, in the first case if I say, that will be greater than K. Why? Because the product is increased, so Q will be greater than K in the first case. So to get that equilibrium back, the product will be consumed and the reaction will proceed in the backward direction so that the Q can be equals to K. Similarly, in the second case, suppose if we remove ammonia, then what will happen? Just think about it. What will happen to the value of Q? Will it be equal to K? No, of course it not be equal to K. It will be less than K, because now you are increasing the numerator value, or you can say you are decreasing the numerator value, not increasing. You are decreasing the numerator value, and if you will do it, that whole part or the Q will decrease, and as a result, to make your Q again equals to K, the reaction will shift forward to increase the value of numerator, which is the concentration of product. Now moving on further, we will take one more example, which is your production of hydrogen iodide. Now suppose we are disturbing this equilibrium by adding H2. Let us look at the same condition with the help of a graph. If you see here, then this is the situation of equilibrium where the lines are straight. Now at this point you add H2 at time t1. You are adding the dihydrogen gas. As a result, what will happen? The concentration of H2 will increase, right? Then after some time, it will start to decrease. You can see that there is a slight downfall in the graph of the H2. It is indicating that your H2 is consumed at this point. Okay, and it is consumed until the line again becomes straight. Now what is happening to your I2 here? Since you are increasing the H2, to make more Hi or to reduce H2, your I2 will also be used, because to make 1 mole of Hi you need 1 mole of dihydrogen and 1 mole of iodine gas. As a result, you can see that the iodine's concentration is also decreasing. So the system is at equilibrium for the reaction, and when you are adding this H2 and you are looking at the different concentrations of the reactants and products, then from the blue line you can easily say that okay, the concentration of H2 is increased due to our addition, and then further it is decreased to maintain the equilibrium. Now what about the I2? What I said about I2? I said that the concentration of I2 will what? It will decrease. And why it will decrease? Because the H2 is now using this I2 to get your Hi. And after some time again, suppose at time t2, there is no net change in the concentration, and at this place your equilibrium is re-established. Clear? So what can you say about this Hi concentration? Just think about it. Is there any change in HI concentration? Now you see that the system reaches a new equilibrium. But the ratio of your product's concentration by reactant's concentration will be same. Although you are seeing a new concentration of H2, I2 and HI, the value of equilibrium constant will be same. So what about HI? I asked you, what about HI? Why is the HI concentration increasing? So it's obvious. You are adding H2. So the H2 will decrease. It will take up the I2, decrease the concentration of I2, and simultaneously when your hydrogen iodide is formed, it will result in an increased concentration of HI. You can look at the green line here. It is slightly increasing and then it is becoming constant after time T2. Now we'll move on to the next change, which is pressure change. To understand this effect, we will take a general reaction in which your A is reacting with B to give us C. All these three states are having the gaseous state. All these three species are having the gaseous state. Now what will happen on increasing the pressure of the reaction? Can you guess it? So if you increase the pressure, that means you are in a way disturbing the equilibrium, right? So to maintain the equilibrium again, the system will favor the side with fewer gaseous molecules. Why is it so? Because your fewer gaseous molecule will result in lesser pressure, and that is directly coming from your ideal gas. We know that PV is equals to nRT. From that you can say that pressure is directly proportional to N. Okay. Now if your reaction proceeds in such a way so that you have at last lesser number of moles, so that will result in lesser pressure. Now we can say that if you are increasing the pressure, then to maintain the equilibrium, the system will proceed in that direction such that it has a lesser number of mole production. So by looking at the equation, can you say that the equilibrium shifts towards product? Is it true? Yes, because on the product side, we have lesser number of molecules. If you consider the reaction, we have two molecules on the left hand side and one molecule on the right hand side. Now if the reaction proceeds further, your two molecules of A and B will give you one molecule of C. So almost you are reducing it to half. Now if you are reducing the moles to half, then you are reducing the pressure as well. Now we will take the opposite case. What will happen if we decrease the pressure for the reaction? Is there any result of it? Yes. Now the system will favor the side with more gas molecules. Why it is doing so? So that the pressure can be again be increased. If you take this given reaction again, then in this reaction, the reaction will proceed in the backward direction so that you can produce more number of moles. Is it clear to you? So we have talked about two situations. First is increasing pressure. If you are increasing pressure, then to decrease the pressure, what will happen? The reaction will proceed in the forward direction so that some moles can be reduced, and as a result, the pressure can be reduced. Similarly, if you are decreasing the pressure, then the reaction will proceed in the backward direction, so to produce more number of moles and hence higher pressure. And this all is being explained through your ideal gas equation, PV is equals to nRT, right? Because P is directly proportional to N, we are doing this, or we are observing this outcomes of the given following reaction. Now suppose we have equal moles on both sides. There is a situation where there is equal moles on both sides. Then what will happen? Then remember, there will be no change in the equilibrium state upon changing the pressure, because on both sides we have the same number of moles. Example, if you take H2 plus I2 giving us 2HI, you have 2 moles on the left hand side, one of H2, one of I2, and 2 moles on the right hand side, which is of HI. So the net change in the number of moles is 0 in this case. So If you are changing the pressure, then what will happen? There will be no shift in equilibrium. So remember this thing, last and the most important point, if your reaction mixture only includes solids and liquids, then in that case, pressure has a negligible change, or you can say directly that it has no change on the state of equilibrium. Remember, this is very, very important to remember. Okay, so suppose if you are taking a reaction in which all the species are present in the solid and liquid phase, then on increasing or decreasing the pressure, there is no net change in the reaction. And that same thing is true if and only if you have the same number of reactant and product gaseous moles, like in this reaction, which is production of HI. Moving on to the third and the most interesting part, I would say. So in this case, most of the students find it difficult to understand the addition of inert gas. Let us try to understand this. Now, there are two conditions. I said it in the start. There are two conditions in which you can add your inert gas. First is at constant pressure. So let's talk about this. So if you are adding an inert gas in such a way that the total volume is increasing and the pressure is remaining constant. So that is the only way you can do the addition, because if you want to keep the pressure constant, you have to increase the volume if you are adding more number of moles. So that is the only way, because PV is equals to nRT. Now you are keeping the pressure constant. So V is directly proportional or can be directly proportional to only one and one thing, which is N. Remember, temperature is also constant. It's only proportional to only one thing, that is number of moles, right? So if you are increasing the number of moles, you are increasing the volume as well. Now, what is the effect of this addition? So all this thing, all this increase in pressure or decrease in pressure is affecting the equilibrium because of the reason that your partial pressure of the reactants and products are increasing or decreasing. Okay, so try to understand this. You are saying that you are increasing the total volume, but you are keeping the pressure constant. As a result, the previous reactants and products will have the same partial pressure. Okay, they will have the same partial pressure. You can think about it, because the vessel is increased, or you can say the vessel is being expanded in such a way so that the pressure which is applied by each and every reactant and product individually remains same. Okay, as a result, there is a decrease in partial pressure. So the system shifts towards the side with more gas molecules. Did you get that point? Is it clear? Just think about it, right? So you are increasing the volume, but the number of products and reactants are same. So they have a greater volume to roam around. As a result, what will happen? The partial pressure of each gas will reduce, but the total pressure will remain same. So this is the situation that we are handling it, right? As a result, what will happen? The system will shift towards the side with more gaseous molecules. Now this case becomes similar to the decrease in pressure, right? So whenever you add a inert gas by keeping the pressure constant, then you are dealing with a situation where you are decreasing the pressure of the reactants and products, and as a result, the system will shift in that direction which has more gaseous molecules. Now what is the second situation? The second situation is of constant volume. Suppose we are adding this inert gas at constant volume. What will happen as a result? This will increase the total pressure, but there will be no change in partial pressure of the reactants and products. So in the first case, when you are adding the inert gas at constant pressure, you are increasing the volume. As a result, your molecules have a greater space to roam around, so the partial pressure of the reactants and products decreases. Therefore, the reaction proceeds in such a direction so that the greater number of gaseous molecules can be produced. Similar to the case of increasing the, I would say, decreasing the pressure. In the second case, when you are doing the same thing at constant volume, you're adding the inert gas at constant volume, then in that case, there is no net change in the partial pressure of the reactants and products. Okay. So what we will say, that as a result, there will be no change in the equilibrium constant. So remember these two conditions. If you are adding at the constant pressure, you are decreasing the pressure, the system will shift to that side which has more gaseous molecules. If you are adding at constant volume, then there is no change in the equilibrium state. What you are adding? You are adding inert gas. Got it? I hope this point is clear to you. If you are not able to understand this, just try to remember this part. That at constant volume, no change in equilibrium state, and at constant pressure, the system corresponds in the same way as it corresponds to decrease in pressure. Moving on to the fourth part, and I would say the most important part, which is effect of temperature change. Let's see what will happen. In this case, we have two situations. Can you remember those two situations? Yes, we have talked about these two situations in your Vent-Off factor discussion. There we have said that if you are doing this for endothermic reaction, if you are increasing the temperature for endothermic reaction, then the reaction will proceed in the forward direction. So this is just a revision for you. Remember this part. And if you are increasing the temperature for exothermic reaction, then the reaction will proceed backward. Let's see. If you talk the same thing in terms of Le-Chatterjee principle, then suppose we are taking your endothermic reaction and we are increasing the temperature. So, to counteract this increased temperature, the system shifts towards product. Why it is shifting towards product? Because the whole process is endothermic, so it will absorb that extra thermal energy which you have provided by increasing the temperature. And it can be only done if the reaction proceeds forward, because the reaction is endothermic in the forward direction. The second thing that will happen, apart from the equilibrium state, is that the equilibrium constant will also increase its value. So this is the most important point. We have talked about this in the Vent-Off factor situation. What will happen in the case of exothermic reaction where your delta H is less than 0? So in that condition, if you increase the temperature, then the reaction will move backward, because if it is exothermic in the forward reaction, that means it is endothermic in the backward reaction. So the extra heat which you have provided will be consumed if the reaction proceeds backward. So we will say that the equilibrium shift towards reactant, or it will shift toward the backward direction. What will happen to the equilibrium constant? You will see a decrease in the equilibrium constant. Got it? Again, that same point, I am putting this point again and again, and you will remember this, that equilibrium constant will never change until and unless you are changing the temperature. Got it? And the change in equilibrium constant is also dependent upon the nature of the reaction, whether it is endothermic or exothermic. Is it clear to all of you? So, this is the only case where you see a change in the equilibrium state as well as the equilibrium constant. In the previous cases, you were only seeing the change in your equilibrium state and not the equilibrium constant. Now, let us take some example. First, we are seeing the NO2 reacting to give us N2O4. So, basically, it is a dimerization process in which your NO2 is being dimerized to N2O4. What can you predict about reaction if you are changing the temperature? So to know that, first you should know that what type of reaction it is. It is basically a reaction in which your NO2 gas, which is brown in color, it is dimerizing into N2O4, which is colorless. And this whole reaction is exothermic in nature, means it is producing energy. So suppose we take this situation in a beaker. What we are doing is we are taking three situations. Let's explore what are those situations. So first, what we are doing, we are taking two test tubes which are containing NO2, and we are keeping those two test tubes in your beaker number 2 for 10 to 20 minutes at 298 Kelvin. After some time, what are you doing? You are transferring these two test tubes to other beakers. that is beaker number 1 and beaker number 2. Now the beaker number 1 is having a temperature of 270 Kelvin and the beaker number 3, not the 2, beaker number 3 is having a temperature of 363 Kelvin. So what is the procedure? First we are taking 2 test tubes of NO2 in a beaker which is beaker number 2 and it is kept at room temperature which is 298 Kelvin. Then you are transferring one of the test tube to a temperature of 270 Kelvin and the second to a temperature of 363 Kelvin. Now let's see what is the observation after doing this setup. So this was our setup. Now if you conclude, then the cold temperature one means the one which is having a lower temperature. If you see that we are putting from 298 to 270, so we are lowering the temperature. As a result of lowering the temperature, your test tube will slowly turn from brown to colorless, because what you are doing, you are lowering the temperature, and whenever you decrease temperature in an exothermic process, then the reaction proceeds in the forward direction, so that the extra temperature which is being decreased can be restored by moving in the forward direction, because it is exothermic in the forward. You can clearly notice that it is not completely colorless now, but it is less brown as compared to the previous situation. Okay, so this is the first condition of the beaker number 1. Now what about the hotter temperature, which is the beaker number 3? In this case, you are keeping it at a higher temperature of 363 Kelvin. Then in this case, you will observe that the reverse reaction is being favored, right? And you can conclude that thing by looking at the color. See, it is now more intense brown, okay? Because since the reaction is endothermic in the backward direction, so the extra heat which you have provided is being only consumed when the reaction moves backward from N2O4 to NO2. Got it? Is it clear? So this is a very important reaction. You can just think about it and you will get that how the reactions are occurring and what is the reason behind it. So only reason is your Lee-Chatterjee principle and your Ventoff equation. So both are affecting this thing. Now next we will move on to the effect of catalyst. Let's see this condition. So catalyst does not affect the position of equilibrium. So this is the first and the most important point. What is the meaning of this? The meaning is that your equilibrium state is not changed, means the equilibrium concentration is not changed. In all the previous situations, you are changing the equilibrium concentration, right? In the case of temperature, you are changing the equilibrium concentration plus your equilibrium constant. But in the addition of catalyst, you will not change the equilibrium concentration, you will not change the equilibrium constant. The only thing that catalyst does is you increasing the rate of backward and forward reaction, right? So it increases both of them in an equal manner. As a result of that, what will happen? The activation energy. So basically this is the energy which is required to complete the reaction. Both in cases of forward and backward, you will need some activation energy. So it reduces that amount by the addition of catalyst, and as a result, the reaction becomes fast. Okay. So what you will remember, that catalyst helps us to reach the equilibrium state faster. It is not changing the equilibrium position or the equilibrium concentration, neither it is changing your equilibrium constant value, right? So it is only affecting the rate of the reaction in a way, you can say, right? You are changing the rate of the reaction, increasing the rate of the reaction. Now we will see what are the effects on K due to changes in various parameters. See, what are the things that we have seen? If I increase the reactant concentration, then the reaction will move in the forward direction to consume that extra reactant. But there will be no change in your equilibrium constant. If you are increasing the product concentration, then to consume that extra product, the reaction will shift backward, but the equilibrium constant will not change its value. Third case, if you are increasing the pressure, right, if you are increasing the pressure, then in that case the shift will be towards fewer gas moles. So you will not decide the direction by just merely looking at the condition. In case of pressure, you have to look at the reaction, I would say the balanced chemical equation as well. But again, there is no change in the equilibrium constant in the case of pressure also. And in the fourth case, when you are decreasing the pressure by increasing volume, then in that case the reaction will shift towards more gas moles, so that the decrease in pressure can be counteracted, right? And this is totally according to the ideal gas equation. Is it clear? So this is a summarized table for two factors, which is concentration and pressure. Now we will look on to some more parameters. Well, just summarizing this whole. In this case, we are seeing it for the temperature. So if you are increasing the temperature for an endothermic reaction, then the reaction will shift forward. First of all, why it will shift forward? So that the extra energy can be consumed. Okay. What will happen to K? Then according to the Ventov factor, we know it very well that the value of K will also increase. Then if you move on to the second thing, which is your increasing temperature for exothermic reaction, then in that case, to counteract that extra increased temperature, since the reaction will be endothermic in backward direction, it will move in the backward direction. What will happen to the K? It will decrease. Got it? Third thing we saw is your addition of catalyst. So addition of catalyst has no effect on your equilibrium state or your equilibrium constant. It only helps us to reach that equilibrium state faster by increasing the rate of both forward and backward direction, right? Moving on to the fourth part, which is addition of inert gas, I would say. So in the fourth thing, the inert gas, if it is added at constant volume, then the partial pressure of the reactants of products are not changing, and therefore there will be no shift in the reaction. And of course, the equilibrium constant will also not change. But if I talk about the inert gas addition at constant pressure, then in that case, the partial pressure of the products decreases. So the reaction behaves in the way like you are decreasing the pressure. So the reaction will proceed in that direction, which has more gas moles. But at last, it has no change on the equilibrium constant as well. Is it clear to all of you? So this was the most important part of your equilibrium, I would say. Most of the questions can be asked from here, and they are asked from here, right? So the theoretical questions from equilibrium comes from this Le-Chatelier principle. So can we summarize all of this? Yes. So increasing reactant pushes the reaction forward. If you increase the product, then it will push it backward. Then if I talk about temperature, then for exothermic reaction, for endothermic reaction, higher temperature is favored, and for exothermic reaction, lower temperature is favored. Moving on to the pressure, if you are increasing the pressure, then the reaction proceeds in the side which has fewer number of gas molecules, and if you are decreasing the pressure, the reaction proceeds in the sides which has more gases molecule. Fourth thing is inert gas addition. If you add this thing at constant volume, then there is no effect on the equilibrium state. If you add this thing in a way which is keeping the pressure constant, then there is a decrease in partial pressure. So it acts like a decrease in pressure. Okay, so the reaction proceeds in that way, which has larger number of moles. What about catalyst? It is not changing the equilibrium state nor the equilibrium constant. It only speeds up the reaction so that the equilibrium can be reached faster. So this was all for today's class. Thank you for attending the session. I hope you enjoyed it.